Hello everyone, welcome to the fourth video of 10 AP Physics 1 summaries. Today we'll be looking at the energy and work unit and focusing on conceptual review. If at the end of this video you're looking for more resources, please check out my description down below for links on more concept review and application problems. If you want to target your time towards specific content areas, I'll include timestamps in the comments for each topic. Let's get started. So what is energy? Of all of the physics unit, this definition is definitely the trickiest. Energy is the capacity to do work or make change, meaning that it's not the actual change itself or the action itself so much as it is an ability. This definition is kind of discomforting at first if you're like me and you like to ground yourself in the concrete and observable, but once you begin working with energy, you'll begin to see why it's such a valuable tool. Energy, sort of like force, comes in many different types. When we do calculations, we're usually working with mechanical energy, which is the sum of all potential and kinetic energy in a system. The main types of potential energy we use are gravitational, and there are actually two kinds of this one, and elastic potential, i.e. spring. There are other potential energies you've probably heard of, like electric and chemical, but for our purposes in this class, we usually just use gravitational and spring. Under kinetic energy, we also have two types, which are translational and rotational. Some of the rotational kinetic energy equations will work with torque, which is in a later chapter, so be sure to check that out if you're interested. Total kinetic energy of an object is the sum of the translational and rotational energy, just as total potential energy is the sum of all of the subtypes of potential energy. We also have heat and sound energy, though we consider these in the context of energy dissipation. One example of this would be a ball bouncing to a smaller and smaller height each time, and this is occurring because its energy is being dissipated through heat and sound. Work is force over displacement. It's basically the go-between for different types of energy, especially kinetic energy. The amount of work done on an object, positive or negative, is equal to the change in kinetic energy. Work and kinetic energy even have the same unit, which is joules. In this example, the Earth is doing work on the falling ball because it is exerting a force weight on the ball over the distance the ball falls. Before being stopped by the hand, the work that gravity did on the ball created an equivalent final velocity. You can also think of this as the work by gravity translating the initial gravitational potential energy into final KE. In the cart example, the driving dog is doing work on the cart over the distance the cart travels, increasing the cart's kinetic energy. Remember that only the force parallel to the displacement does work. Force that is not parallel to displacement does have an effect, but it isn't work. A classic AP Physics trick question asks about the work done by gravity when a planet orbits the sun. There's constantly force exerted by the larger body on the orbiting body, and also vice versa, and the orbiting body constantly has angular displacement, so where's the work? The answer is nowhere. The perpendicular gravitational force is changing the direction of the planet, but there's no parallel component. This makes sense because in the example, there is no change in the orbiting body's speed or kinetic energy. Since kinetic energy is the same, it's a good indicator that no work has been done. In this next example, we're reminded to be consistent when defining displacement and force. If we multiply the literal displacement, which is the yellow dotted line here, times the literal force parallel, which is this component, we get the same answer as if we multiplied just the vertical displacement, which is this orange dotted line, times the weight force. I would encourage you to prove this to yourself if you have time. The funny thing about energy questions like these are that there can be multiple right ways of finding the same answer. You can never go wrong with force parallel times displacement, but in this example, to simplify it for myself, I would recognize that the work is ultimately translating the initial gravitational potential energy into final kinetic, and therefore I would personally just look at the vertical displacement and weight force. When we see graphs, always consider what the relationship is between the independent and dependent variables. I see force and displacement, I think work. If we have a graph of an object's force over its displacement, then we can find the area between the curve and the x-axis to find the work done, since it's the product of the two variables. In this example, we get these four geometric sections. Note that any area under the x-axis is negative because the force is in the negative direction. Because of this, red and yellow of equal magnitude and opposite sign cancel out, and we're left with the work equals the energy gained, which is equal to the green area plus the blue area. The first major energy that you'll work with is kinetic energy, which is the energy of motion. There are two major types of kinetic energy, translational and rotational, and many moving objects often have both. In translational kinetic energy, a force over a distance does work on an object and changes its linear velocity. In rotational kinetic energy, a torque over a moment arm does rotational work on an object and changes its angular velocity. There'll be more on angular motion in later sections. An example would be that if you have a can rolling at a linear velocity and another can sliding with the same linear velocity, the rolling can has more kinetic energy because it also has the translational kinetic energy from the linear velocity and the rotational from rolling. Do not forget that rolling objects have two types of kinetic energy, rotational and translational. If we have this blue mass and it rolls across the screen, then we can break this down into the rotation aspect and the translation aspect. Up here we just have our unit analysis that shows kinetic energy is in. Gravitational potential energy is the energy of height. Because of gravitational forces, objects are constantly being pulled towards each other. Therefore, when objects are not allowed to just free fall into each other and are instead held at a certain height away from each other, we see this concept of potential energy. When released, gravity would do work on the objects, but when they're held apart, gravity, a conservative force, only has the potential to do this work without actually doing it. There are two different types of UG, one is much more frequently used than the other. We usually work with UG equals mgh, though there is also a version involving big G, the universal gravitation constant. You see applications of the latter in problems involving space, but the principles are the same for the two equations. You can easily derive both forms of gravitational potential energy by recognizing that work is the change in energy and also the force over a distance. So any UG is just its FG counterpart times the distance it would be exerted over. In mgh, we take mg, the weight force, and multiply it by the height, the distance the work would be exerted over when the object is in free fall. In G big M little m over r, you take Fg, general, and multiply it by the radius of the distance between the two masses it connects. In unit analysis, we see that Ug is also in joules. Elastic potential energy is the energy of stretch and compression. When you stretch or compress a spring, the restoring force gives the spring and object attached the potential to do work by tending to go back toward equilibrium. If this pink block is at its equilibrium position here, denoted by the yellow dotted line, and it's compressed by this red displacement, we treat the red distance as x and calculate the potential work the spring would do when returning to its equilibrium upon release. When an external force does work on a spring to compress it by displacement x, then when the spring is released, all of the US that the spring was given by the work translates to kinetic energy when the object is at equilibrium and there's no displacement to give the spring US. Simple harmonic oscillators like this one often come up in energy conversion questions, which we'll take a closer look at in video 6. For elastic potential energy, the key concept is displacement from equilibrium gives elastic potential energy. Again, unit analysis shows that elastic potential energy is in joules. Here are the essential equations for each type of energy. Pause this video if you want to write them down. Alright, the big guy. The law of conservation of energy is the number one concept for this unit. It states that in a closed system, the sum of all energy initial equals the sum of all energy final. In an open system, i.e. anything where we could say that a so-called external force does an action, energy is conserved, but it is not constant. This means that energy is not just created out of thin air, it comes from outside the system. For example, if we consider the earth, floor, a book, and a table for our system, and I come and lift the book onto the table, I'm an external force that does work on the book and adds potential energy to the open system, specifically gravitational potential energy. I used my chemical bodily energy to do this action, so the energy did not just poof into my hand. Energy was conserved. But because I'm outside the scope of the system, the energy within the system is not constant. As another example, if we make our system a block falling off the edge onto a spring where it then oscillates, there's no external entities that would do work on the system, so the total energy initial should equal the total energy final. For one final example, with the same general situation, except instead of bouncing off a spring, the block just hits the ground and stays there. In this case, energy is still conserved, but it is dissipated. The collision between the block and the ground release energy as heat and sound dissipating into the environment. Note that energy is not destroyed, just dissipated. It is never created nor destroyed, only transferred or translated. So if you start with X amount of energy in a closed system at the beginning, you should be able to track this energy to the end and account for every last bit of it. This brings us into energy accounting. This is the equation equivalent of what I just said. The sum of all forms of energy initial should equal the sum of all forms of energy final. If we look at this example and these equations, we realize that in every stage we can track the forms of energy present. The man does some initial amount of work on the ball to give it kinetic energy, both translational and rotational because it is rolling. And the ball also has initial UG by virtue of its position if we use the ground reference as height equals 0. Then the ball gains more kinetic energy as it falls, translating its initial UG into KE. As it compresses the spring, there is elastic potential energy, and that is thrust back into the air, ending with only gravitational potential energy at its peak. If there is no friction present, then this final height should be greater than the initial, because it translated the initial kinetic energy into just more gravitational potential energy. If the ball instead only reached a maximum height equivalent to the height it started rolling at, we would assume that there is some dissipation of energy from friction, because we have to account for the initial kinetic energy component when energy accounting. This is just one way that conservation of energy can come up. You may have to isolate one term in this master equation. When working with gravitational energy in particular, be sure to choose an appropriate reference frame for height equals 0 to simplify calculations. If we have a question about an object falling off a cliff and we want to find the final kinetic energy right before it hits the ground, we would likely set the ground at h equals 0 so we can easily calculate initial UG. If we instead have an object oscillating on top of the same cliff without falling, you would use a different reference for h equals 0. You'd probably set the top of the cliff as h equals 0 or maybe even the bottom amplitude of the oscillation because it simplifies calculations. There is no reason to account for the UG that exists between the object and the ground below the cliff because this is not in the scope of the question. Because there is no absolute reference for UG, make your life easier for yourself and choose references that make sense. This same premise shows up when we ignore thermal energy in an object from its temperature or rotation around a sun when calculating KE of a regular car driving on the street. It just doesn't make sense, so take the liberties you need to while remembering the important energies in a system. Power is the rate work is done with respect to time. It is not a major concept, but you should be familiar with it. Because work is equivalent to change in an energy, usually kinetic energy, power is also expressed as delta E, but this time over T. Let's look at some examples. Who has more power, the woman shoveling the snow or the child? Probably the woman because she's doing more work, i.e. lifting and throwing the snow in less time. Now here, who has more power, the horse or the dog? Most likely the horse because it can do more work, which is moving heavier loads, changing the load's kinetic energy in less time. And finally, we have energy in collisions. The essential idea is that objects involved in elastic collisions have a KE sum equal at the beginning and at the end. Inelastic collisions, on the other hand, do not have equal kinetic energy at the beginning and at the end because energy is dissipated when objects deform and produce heat. The cars obviously deform, whereas these billiard balls do not really deform, so they are good tellers that a car crash is inelastic, whereas billiard balls are often used as examples of elastic. We'll work more with collisions in the next unit, momentum. Okay, we made it. In my next video, we'll move on to Content Area 5, Momentum. Thank you so much for watching, and be sure to check out the description for more resources and more about me. I'll catch you in the next one for more AP Physics 1 content.